Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi all, thanks for coming. It's my pleasure to introduce John Canny today from Berkeley. He's a professor of computer science, and his research is near and dear to our heart because he marries HCI with machine learning, with signal processing, and even big data. And he's focusing these days on health and education primarily. He'll be talking to us about those topics today. And some news about Berkeley. John's participating in sponsoring the creation of a Jacobs Design Institute, which is supposed to open next year?
I said, I did say next year, 2015.
2015,
sorry.
So that's kind of cool that that's happening soon. So welcome, John.
Thanks, Mary, and thanks for the chance to talk to folks. So today I was going to talk about some work we've been doing for a few years on the opportunities of sensing without sensors, or at least without things that we normally recognize as sensors. And most of the work has been directed at sensing some sort of affect. Most of our work has actually been on stress. We did a little bit of work on pain, and some work that had a focus on depression and mental illness. The signals, though, are quite similar that we end up being able to detect. And we're currently starting to move from the sensing and detection into interventions based on what we find in the sensor data. So to quickly review stress is a very important and very global regulatory mechanism in human beings that helps us function at enhanced performance when we need to. It's how we pull all-nighters and make conference deadlines. But it has negative effects, obviously, as well if we leave it on too long. Because basically our stress mechanism is a trade-off between fight and flight ability, our ability to respond accurately and sort of exceed our average potential briefly, and all of the important regenerative and repair functions that we need to do as well. It's a complex system, but roughly there are fast and slow components of the stress response. The fast one is the adrenaline or epinephrine response, which is when we get excited, our pupils dilate, we are ready to spring into action, and it happens very fast for obvious reasons. If you're going to fight or flight, you probably should do it soon. And then there's a slower response, which is to do largely with shutting down or sort of toning down the rest and digest functions. And so this mechanism is perhaps the one we should be most concerned about, because when that kicks in over long periods of time, that's when we start to have trouble. Okay, so two different physiological responses, and they tend to have two different types of signals that you can observe in the body in response to them. And I'll just clarify for those of you that know, in both cases I'm talking about parts of the sympathetic nervous system. So both of these parts are enhancing fight and flight and reducing rest and digest. There's a complementary system that helps with your regenerative functions, but we're only talking about the negative side, or the stress side, I guess, on this slide. All right, so we have these fast chemical mechanisms, and then the signs that you see in the body are heart rate increasing with fast stress response, and breathing speeds up, pupils dilate. We improve memory retention and some types of recognition, and our emotions are typically intensified, amplified. And then the slow mechanism, interestingly, the heart rate variability, the sort of variance in heart rate changes with the slow stress response. We get galvanic skin response changes, little pulses effectively of changes in skin resistance with perspiration. breathing becomes more eccentric often, and we have muscle tension. So when we say we feel tense because of stress, that's not just a kind of an illusion. We really are tense. Many muscles in the body become tenser in response to stress. So heart rate variability, although we're not primarily trying to measure it, this is the gold standard that we do in the sensorless work. So just to quickly review what it is, when we talk about heart rate variability, we're typically talking about different measures of variation of the interbeat interval. So, and this is a very complex topic. There's lots of different measures. The simplest one to understand is just the variance or standard deviation in that actual number from a suitably measured peak in the heart waveform. The others are quite a bit more difficult to explain. Low frequency, high frequency ratio, which requires us to Fourier transform the interval signal. But anyway, this one, the first one, is easier to measure, but it's harder typically for to provide physiological justification for. Biological arguments have been made that this more complicated measure directly measures the ratio of the sympathetic or stress response to the parasympathetic or rest digest response. So yeah. So I'm bringing it up. We'll say more about it later. It is a measurement that we made as part of our study of sensorless sensing. And the hardware we use is an older project called the tricorder, Berkeley tricorder. And that was a custom sensor that we started building, I think, about 8 years ago. And you can probably see some dates on here. This is a 2008 version. It recorded all of these vital signs. So in particular, we had a heart waveform signal. And it would both store the data on a flash card or also stream it out on Bluetooth. And it recorded a lot of other measures that we didn't use for this study. Okay, so having done the work on the tricorder, by the way, we became quite enamored of the idea of not using hardware sensing. Hardware sensing is obviously hard to do. It's challenging. There are lots of adoption challenges, even with fairly simple technologies like wristwatches and so on. So we really started to focus on measurements that we could make implicitly from people using existing electronic devices in the way that they would normally use them. So we did some work that I will describe on monitoring of voice on a cell phone, typically during phone calls. And we also have a sensor in our lab, which I won't talk about, but we have the ability to also do both location analysis and also affect analysis on voice signals of people in the lab at Berkeley. And the most interesting stuff, which is current work, is looking at motion sensing from the mouse, from people using a mouse on a desktop, potentially using a trackpad on a laptop, which we haven't done yet. And another similar kind of signal, which we do have measurements of and which we're analyzing right now, is the accelerometer on a phone. The phone's quite rich, and it includes study use of the phone. We're interested both in the passive signal of somebody just holding the phone in front of them and looking at something, the tapping signals from interacting with the screen widgets, dragging and so on. All of these produce a signal that can be analyzed in a similar way to the mouse signal. And finally, there's a lot of opportunities. We're not pursuing this, but a number of other people. Actually, one of my former students has been recently looking at camera sensing on cell phones for pulse measurements for stress also. There's a lot of opportunity there. We're not currently following that, though. Okay, so speech encodes stress in an interesting way. It's without, I'm not an expert, but as I understand it, part of our response to stress is for the vocal cords to pull away and basically open up the breathing passages so we can suck down more air rapidly. So those stress-related muscles actually pull on the vocal cords and change the shape of the glottal pulses when we speak. And this particular signal happens to be very accurate at predicting stress. We got about a 95% accuracy, and what we were measuring was a controlled experiment where we deliberately stressed the subjects and had them in an unstressed state, and then we looked at the accuracy of this signal in predicting which state they were in. So it would be nice, it's desirable to do analysis of that signal on the phone, but it turns out to be computationally challenging because it has a fairly complex inverse problem to solve. Because we're interested in this signal, which is the vocal cords basically flickering, I suppose, that's the signal that produces our speech. But before we hear it, it goes through the vocal tract, and basically a complex filter is applied by the way we shape and make phonetic sounds. So what comes out is a lot more complex than the little pulses, more or less isolated pulses that are going in. So the task to do this analysis on a cell phone is to model and invert this transpose. So notice that we don't know what the filter function is because it's varying as the shape of the vocal tract varies. So we have to both estimate it and then try to undo it. Yeah.
So when you say 90% accurate predicting stress, you mean
Yeah.
the short-term stress, right?
Yeah, I mean stress that we were able to induce with math problems. Yeah, short-term stress. Well, okay. To be a little bit clearer, there are both kind of probable adrenal and probable cortisol responses in the stress response that we measure. So it's not purely short-term. And in fact, a lot of the experiments we've done have had more than a 5-minute lag between the stressor and the measurement, so they're more likely to be from the slower response. Yeah, okay. Well, this is more detail than I need, but there are a lot of features that contribute to stress analysis. The one that works really well, though, is the one that's not on this page, which are the glottal features. Those are the ones that are deconvolving. So to remind you, those tend to be more than all of the other ones on the other screen combined. So we basically did some work on accelerating, so that we have an architecture for doing general speech analysis with all of those features. But the features on that list were fairly easy to implement because we used an existing toolkit called OpenSmile. Yeah.
So how do the kind of classification features that you're looking at differ from like NLP recognition? Like
Well,
what types of things they would look at?
So some of them are essentially, it's a broader set. I mean, speech recognition tends to be built on HMM models on the MFCCs. The MFCCs are more or less the standard features at the front end of a speech recognizer. The other ones tend to be, pitch per se is considered more of an affect signal than a speech recognition signal. A lot of these things are the people that speech recognition people try to avoid because this is highly variable between male and female speakers and children and so on. So speech people try to, in a sense, speech recognizers try to factor out those effects. But we're very interested in them from an affective point of view. But for pure speech, these are basically sort of filter banks, nonlinear filter banks. And then they go through HMMs to basically track the little trajectories of phoneticization of speech. When we do recognition, we're actually using these more as like static features. So again, getting more at this kind of general average shape of the vocal tract, which is probably a better cue to affect than the dynamics. But there are some dynamic features that we, so my student did a course project, and one of the things that he was trying to measure was using the speech features and a simpler HMM, basically measuring speech rapidity, so, the number of phones per minute, and also the durations of pauses, because pauses are also a sign of stress. Diminution of pauses is a sign of stress as well. So Yeah, there's a little bit of stuff that you can get from higher level phonetic analysis of speech, but we didn't do much of that. And we didn't do any analysis of the content of recognized speech either, which could have also been a good signal. Yeah.
Stress, you also have a normal tone of speech as a feedback, like then you use this sort of as a reference and able to detect whether it's stress.
Yeah, so so 90% I'm saying the experiment was a counterbalanced experiment where people would either start off, or they'd either be sort of pressured into a stress state and then relaxed, or they'd go the other way around. And so we were comparing the two signals for each I'm sorry, actually, no, the 90% is a speaker-independent measure. So it's actually a very, very strong measure. I need to keep the experiment straight. So that was a remarkable thing about our work and the work before, which is the stress measurements are actually speaker-independent. So they're surprisingly strong. The work I'm going to talk about later is trained per subject. But the vocal speech features are robust, and you can get those accuracies in a speaker-independent way, surprisingly.
Pitch you just mentioned.
Yeah. No, it's not. Yes. So that's not.
The normal tone and you stress that they are quite different.
Yes. So the point is that almost all the recognition is based on most of the accuracy comes from the glottal features, which are much more speaker independent. The changes in them are more speaker independent. So, yeah. So. Those are good questions. So here's the framework that we built onto a phone platform. These, again, most of the features came from the OpenSmile toolkit, which is an open source speech processing toolkit. And our classification was just simple. It was linear SVMs built on those features. And the toolkit, I think we have the accuracy figures with, let's see, where are we? Yeah, so these figures, by the way, are for recognizing a discrete set of emotions rather than stress. The numbers are lower, but also they're multi-way classifications, so you'd expect them to be lower. The numbers for the stress figures down here are with and without those glottal features. It's a bit misleading because you see only a 1-point increase. The point is, though, that that's a very large increase at that level of accuracy. And also, when you look at this recognizer, it's using mostly those features. So they do contribute a lot to recognition. But it's still worth pointing out that the stress feature is actually remarkably strong compared to, say, recognition of emotion. Recognizing stress is relatively easy. Certainly for machines, probably for people too, I suspect, if you really ask people. A lot of people I know claim that they can tell, certainly relatives claim they can tell when I'm stressed. So, okay, so that was some work we did earlier on recognition of stress from voice. I should point out that there was related work by others at Georgia Tech on actually discriminating depressed and non-depressed patients from very similar signals, and they also attained accuracies in the 90s for detecting depression, chronic. But their population they had a control group and a clinically depressed group, and the signals were very strong between those two. Yeah, question?
Yeah, I certainly feel like my stress level's kind of continuous. I'm a little stressed or I'm not stressed.
Yeah.
Do these signals operate in that same way? Or?
Yeah, so all of the measurements are going to be quantitative measures. So I'm quoting accuracies in order to give a, well, actually, these accuracy measures here are, assuming some sort of threshold's been set. Rock area is kind of a measure that is capturing the accuracy as you vary the threshold. So rock area is normally used for a quantitative measure of some kind of feature, and it tells you that this should work over a range of different values. So it is a useful quantitative predictor. Okay, so the most recent work we did was on motion sensing, because the voice work is interesting, but there's a number of issues with it. It requires somebody to speak at regular intervals if you want to track stress. It can potentially, well, it suffers from the usual challenges of speech, which is people will often do it in a noisy environment. In fact, people will deliberately avoid often quiet environments like their office, so they don't disturb people. And on the other hand, things like computer keyboards and mice are tremendous potential tools for sensing because people use them so much, and they're using them also in a context where their potential stresses are actually hitting them at the same time. So, so we started looking at phone sensing and, at mouse sensing and phone sensing. So we have a system called mouse stress, which looks at the stress-induced increases in muscle tension. As I mentioned, there has been work documenting stress, certainly in the neck and shoulders, but also in the arms. And people have specifically looked at stress during computer work. So there's a very large literature on this. This is just a couple of references that have kind of told us the obvious, that yes, people do have muscle tension when they're stressed, and it's measurable. So, so we're in good ground for trying to do this. And so then to the study, our goal was to see if we could measure stress by looking at fairly typical mouse movements, such as moving and clicking, dragging, and steering. Steering maybe is a less common one, but does show up. Steering, kind of mechanically, it's one of the best ones for making the measurement. It's not as common, but it would include things like tracing your way through kind of nested pop-up menus. So we have not yet done a naturalistic study on real interfaces. We did a more, I suppose, theoretical study where we had controlled tasks with varying distances for people to move and varying size targets. So those had similar dimensions, similar geometries for the clicking task and for a dragging task, where the idea was to move that target onto that one. And the steering tasks look like this. These are also common tasks that people have used often in other studies of mouse performance. So our target sizes were in factors of 2 across a fairly large range of, this is pixels, so but a big fraction of the screen, perhaps a fraction of an inch to several inches for the movements. And I guess there were 5 different values for distance and 4 different values for width. Again, more or less very similar to what people do in other types of mouse study. So when we want to analyze the mechanics of mouse movement, we adopt a very simple but nevertheless fairly widely used mechanical model, which is a spring mass damper. So in biomechanics, it's fairly common to consider muscles more as adjustable springs rather than than some kind of motor that's applying controlled force. It does seem like muscles, when we activate them, that we typically activate them in pairs with a set point. And there's some biological damping that causes the muscles not to oscillate when we do that. So it's a simple system. It's characterized by a second-order differential equation, which means that basically it rings with a diminishing sine wave. So that's all we need to do. We want to, though, infer those models somehow from the data. And the data is going to look like this. These are some recordings from, in one dimension, from those mouse movements. It's interesting, you can see people very visibly hunting and making several different adjustments most of the time. But the dynamics of the models are encoded in the curvatures of these little segments here. And we use LPC, which is a standard signal processing technique, in order to infer second-order models that match those trajectories. Yeah?
Is the model valid for different types of pointers, so for touchpads or for
Would the model still be the same?
Well, because we're trying to model the arm itself, intuitively it should work if with any sort of position sensor or velocity sensor or acceleration sensor, because it's really the mechanics of the arm rather than the. But if somehow it's I see what you're saying. Yeah, if it's a tracking device that doesn't involve perhaps movement of the arm, then yes, we have to look at that. The hope would be that because the muscle tension seems to be a fairly global kind of an effect, it might also apply to fingers, but that would be worth checking because it's not obvious that would work. So from this, we fit the second order model. So LPC is a model that's commonly used to fit second order differential models to signals. It's very efficient. You basically just need to extract a few local correlation coefficients from these signals, and that gives you a second order LPC model, which has a very simple relationship to the parameters of the spring mass model. So these are parameters that you can get from the LPC model, and then those translate directly into stiffness and effective mass of the mass model. In other words, we can observe a trajectory, generate these second order LPC model coefficients, find some roots, and then derive mass spring damper parameters. And none of this is expensive to do computationally, so it's easily done as a little background process on a PC. So we designed an experiment to try to quantify the accuracy of this, and it was a counterbalanced design. Our goal was to have for each subject, because we didn't know how strong the signal would be, we wanted to have some measurement periods for each subject where they were in a stress state and an unstressed state. But because it was a 1 hour experiment, it was rather compressed. So people would enter the experiment and have a calming phase to try to get everybody to a similar state. And then they had to do a challenging math task, which was stressful for most people. Then we did the first mouse measurement where they were given these pointing and clicking tasks, pointing and dragging tasks. Then there was some kind of calming exercise given to them for 5 minutes. And finally, there was a second mouse measurement phase and the final exit calming required by our IRB. So that's the first condition for subjects, and half of the subjects were in the counterbalance condition where they were given an effective calmer first, then given the mouse task, and then finally the stressor in the second phase. So one thing to note about this design is it wasn't ideal in terms of giving us the best stress signal to measure with the mouse, because we actually had separate phases of the stressor itself from the mouse task. So the measurement and the stressor weren't actually concurrent. And that was a choice we made in order to make sure that we had a very good sort of robust stress signal here. We basically used a task where people were concentrating on the math problem that was similar to what people had used before in other stress studies. So we could have tried to give them a mouse task at the same time, but the concern was that might have distracted them. Maybe they weren't really stressed. We thought it was safer to produce real stress, which we could validate with self-report and HRV measurements, which we did, and then see what we could get from the mouse analysis later. So we expected a certain amount of decay, and in fact there was some decay of the stress signal during the mouse measurement phase, but it was nevertheless strong enough for us to get reasonable results. In fact, it was considerably better than we had expected. So I think this is all just saying what I just said. So, yeah. So we wanted, again, to have a validation that the stressors were really working. So subjects were given self-report questionnaires at beginning and ending of each phases. It's important to point out. That was sort of for practical reasons we had to give them the surveys when they were transitioning from one behavior to another. those were very reliably significant. And you can see that although there's a label here saying the stress and the surveys were taken at stress and calm stages, what actually those numbers represent are the averages of the questionnaire. Sorry. Those are actually the average of the questionnaire responses at the beginning and end. So we called the stress questionnaire response the value averaged between here and here. So it was supposed to be something in the middle here. Similarly, the M stress signal was an average of the readings before and after the phase. Okay. All right. So what we observed was that the difference in stress was higher during the active stress phase relative to the calming phase. So about twice as, the difference is about twice as big there as it was here. So about roughly a 2-point difference versus a 1-point difference. So in fact, there was some decay of the stress signal, over time once the stressor was removed. So heart rate variability, we were measuring continuously. All of the subjects were hooked up to our tricorder instrument, and we measured heart rate variability. And basically the results are sort of all over the map. We worked hard to get them to be a bit cleaner than this, but a reality of heart rate variability is it's a very difficult signal to get consistent answers out of. Every reference we've seen on that on the particular instrument has similar results. The best result was actually for the fast stress response. The basic heart rate difference was the strongest signal, not the variability at all. Yeah, there was a huge difference in the two measurements. So we actually went over the data a number of times to check that, and it's actually it's a very strong signal, and it's really there. Realistically, none of the other measures I would say reliably reportable. Although we have some significant results here, we've got we took 7 different measures, and if you really want to have a significance of 0.05 when you're taking multiple measures, you need to correct, and the thresholds would drop below. You really should be working at 0.05 divided by 7. So these effects, aren't really strong enough to be reported. You're having too many chances to succeed, I would argue. The other rather disturbing thing is that these signals were arguably, that marginally significant maybe is one way to say it. There were some others over here, though, which were, especially this one, and there's one up there too, which are actually about as strong, and they're in the wrong direction. So heart rate seems to be saying people were more stressed in the calm phase. And again, we went over this data a lot, and while there are some outliers, a lot of it is coming from a little bit of motion artifacts, which we weren't able to sort of reliably eliminate. That is, we couldn't define criteria that said we can throw this data out and keep the other data. So the high order message is that we tried our best to get good HRV results for this data set, and we got one, which was actually a fast stress response. All of the others, I'd say, are not credible. And the last thing to say is that when people do heart rate analysis, all of the formal work does involve hand cleanup. So it involves trying to eliminate the worst phases of non-signal and the worst outliers of these values. And in spite of doing that, we still didn't get a reliable signal in heart rate variability. So yeah, so there were several measures, but if you actually factor in Bonferroni correction, they were less strong in the M stress, but none of them, I think, were reliably reported, and some of them were actually in the wrong direction. So not a good result. All right, so now to the, the measures that were derived from the dynamic measurements from the mass spring model. Here we got much more credible results. And just to remind you, these measurements were made in the aftermath periods, M stress and M calms, which are actually the intervals right after the stress or the calming influence. The absolute values of the signals are pretty small, but you'll see on the graphs that those are actually, the parameters themselves are clustered around those values, and when you see differences like that, they're actually quite good. So we do get a reliable difference and a nice strong p-value, and they go in the right direction. In other words, people are more tense when they're stressed. And these are just simply some different parameters. These are the actual frequencies of the damped response. These are the damping parameters. It was less clear whether damping parameters should be smaller or larger when people are stressed. And our results were not really very conclusive on that. And as a reality check, you might expect people to be a little bit faster when they're stressed, but we didn't get a robust signal endorsing that. In fact, we got virtually no signal. Okay, so, and that, what I just showed you was the aggregate across all of the pointing, dragging, and steering tasks. It didn't matter if you broke them down. They were individually significant in all of the cases, as long as you use the frequency features. So, yeah, so it seems like there's a real signal there. We didn't get a signal from time, surprisingly. All right, so let's look at the signals a little bit more. One really nice feature that we noticed of the stress signal as a function of task is that it had a visible and significant sensitivity to the distance of the task. So just to recall what the tasks were, we had in all 20 tasks, 5 different distances and 4 different widths in powers of 2. And they're shown along here. This is the 5 different distances. These are the distances here, and these are the widths of the targets along here. And you can see that there's a clear dependence on the distance and close to 0 sensitivity on the width. So quite different from a Fitts law kind of a sensitivity. And what that allowed us to do, but you can also see a nice separation between stress and no stress. But you can also see that it would be important to model the sensitivity to task if you want to really distinguish these things. There's no separation if you confound for task.
Did you look at these by index of difficulty, Fitts law index of difficulty?
Well, I mean, we could, because the Fitts law index of difficulty, well, you'll see in a second, the time follows exactly the index of difficulty. But no, the index of difficulty is basically the distance divided by the width. So that's a sawtooth. It's a sawtooth going like that. And basically, it's only half right. It has the right sensitivity to distance, but the completely wrong sensitivity to width. So it just argues for a different model, different and simpler model. And that's what we built. And we found similar results for dragging. The dragging curves look like this. Again, virtually no sensitivity, maybe a very slight slope. We actually didn't model that. We just modeled the distance sensitivity. And there's a good reason for that. Let's see. Finally, yeah. So we turned this observation into a model where basically we extracted we fitted a parameter alpha based on the log of distance. So the other thing to observe here is that these steps are constant in size, and the target distance is varying exponentially. So it argues that the right model is alpha times the log of the distance, similar to Fitts law, but again without the width sensitivity. And from that, it's very easy to derive what alpha should be. And in fact, we use an alpha that's independent of the subjects. So I'm sorry, actually, I didn't quite, I was out of sync. So this is the dragging task here. The other ones were still for the pointing task, but you can see it's the same kind of shape. The steering task, though, it was more like a Fitts law type of sensitivity. So this one did show sensitivity to the target width as well as the distance. Again, though, with a apparently logarithmic dependence. So we did analyze the steering task using this more complex model that had both width and distance parameters. And finally, time looks like this. And if you work it out, these values are just proportional to the index of difficulty from the numbers below. But here, it's also kind of obvious that there's very little or no separation in the time signals, which was a bit of a surprise. All right, so now we have something, a very simple model, but nevertheless a model that's easy to compute, which is we can take those raw readings and basically subtract off the stair effect, which in the case of pointing and dragging was, or clicking and dragging was, independent of W, just depending on D. And the numbers that you get out are sort of then normalized, and you can simply apply a classifier between them. Is that making sense? So we basically removed the staircase dependence. So now if we had any observation, as long as we know what the distance of the movement was, we could produce a kind of a canonical measurement, which should be different for the stressed and stress case. So from that data, we finally run some kind of a classifier and derive some accuracy results. And here's the result of that. We tried a few different ways of classifying. The simplest one is just taking the stressed and non-stressed points, taking the mean of them. These measurements, like the HRV measurements, still have a lot of outlier problems. So taking mean values is a very bad model. We instead used a max accuracy classifier, which simply means we took the threshold. It's a one-dimensional signal now. So we took the threshold which gave us the highest accuracy, which would be equivalent to doing a support vector machine on one dimension, but it's just simpler to take the highest accuracy threshold. So that's what the blue curve is here. The red curve is taking a simpler threshold, which is just simply the mean of the two sets. So taking a sort of an average midpoint between stressed and non-stressed populations of data. Both of those are using the stair model. If you take the stair model away, you get this accuracy here. And to be more specific, I think it says it here, but the measurements are made by taking our experimental data, randomly taking a sample of some of the points as the test set, and then training the model, meaning just setting the threshold on the other points. And finally, using the trained threshold to classify the held out points. So along this axis here is the number of held out points, the number of sampled points. There were only 100 points in total. So the accuracy is generally increasing as the sample gets bigger, but at some point it tapers off because you don't have enough data from the model. The model is the other points. But anyway, we get about accuracy of about 70. This is per user. So given, let's say, a few hundred points of data for a user, you can generate, assuming it's labeled as stressed and unstressed, or perhaps it might be labeled as neutral, you can learn a threshold, and then from about 10 observations, subsequent observations, you should be able to classify stressed and unstressed to about 70% accuracy. Again, to remind you, the data that we were using was based on the state of the subjects in the M-stress and M-calm state, where they had perhaps fairly modest levels of stress. Perhaps from the self-report and the HRV data, roughly half as much stress as during the full stressors. So, yeah, and the data for the clicking and steering task is here. We get similar results overall. This one's a bit lower, that one's about the same. So around 70% accuracy again. So, it seems good enough for practical use. And a key advantage of the models, the staircase models for clicking and dragging, are that they don't require knowledge of D. That's extremely useful because if you build a very simple logger that's application oblivious, that's just running at low level, looking at mouse activity, all the logger has to do is recognize the start and the end of a mouse movement, let's say with a time window. It doesn't need to know what the target size was in order to figure out the stair correction, because it's only depending on the distance. You only need the distance value. Presumably, because it has that really nice logarithmic dependence on the values that we were able to take, you should get a fairly accurate measurement by taking the log of some distance, which wasn't one of the ones we did. So we are actually in the process of doing a subsequent study with more realistic mouse tasks, where we simulate angry messages from people's supervisors coming in email to produce the stress in an actual GUI context, so we can get more realistic movements. But still, there's pretty good evidence from the study that should work. So so we are building this revised logger, which will run as an independent process, won't need to be linked to applications, which has some privacy advantages as well. But simply by looking at the lengths of mouse movements, it should be able to report a value that's an estimate, kind of real-time estimate of stress. So our original goal of this was sort of health, lifestyle related. How can we help people monitor stress? But it does suggest that perhaps we could generalize a little bit in our goals and look at things like people's levels of frustration or perhaps anxiety about user interfaces or applications. In the absence of measures of what the stressors are in people's lives, if we simply look at these stress levels as a function of time, and if we're able to get a little bit of information about which app people are running, then we can use this kind of measurement as a kind of an implicit usability measure, which I think would be pretty interesting. So, it's simple enough we could get masses of data, and depending on how you cross-cut that data, you can isolate factors such as the application that people are running and get perhaps this implicit usability information. All right, so that's the summary. I'm just going to wrap up there. We have generalized to a cell phone. We've collected some data from a very similar study with the cell phone. The only difference in the cell phone is the tasks are both more diverse and less controlled, meaning we did do some pointing and dragging tasks on the cell phone. On the other hand, though, we observed, and we have video of the experiments, that people's use of the cell phone was a lot more diverse than the use of the mouse, and that people sometimes would rest a hand on the table, would sometimes hold the phone up. In some cases would be holding the phone in two hands and doing tasks. So in terms of the dynamics, it's a lot more complex, and most likely we'll have to do at least attempt to recognize the distinct mechanical states that people are in when they're using the phone. Nevertheless, there's some signs that certain types of feature, the basic tapping on the screen, seems to have a really nice dynamic ringing signal that seems to be related to hand tension. So, all right, so that's still work in progress. Hope to have that soon. All right, so to summarize, we've been working for a while on sensorless sensing, which is trying to leverage existing technologies, some of which seem to have remarkably strong signals around affect generally, but especially for stress. So we described recent measurements on mouse stress, which is a ubiquitous, low-cost, hopefully reliable source of stress data in the real world from ordinary mouse use. We'd like to see if we can get similar measurements from cell phone use, and this we think would have advantages over the voice-based cell phone use in that they would be applicable to people holding the phone, which they arguably spend a lot of time doing And we'll have to see if the environmental vibrations and so on are tractable or not. So yes, and of course work that my student Pablo is doing and Mary's group is doing is looking at interventions and trying to tie some of these measurements back and deliver appropriate, timely and effective interventions for relieving stress and improving mental health. Okay. Cool. Yeah.
So another common sensor is the camera.
Yes.
The camera on the phone. Do you
Yeah.
have any plan for some using the visual cue?
I don't currently have a student who is oriented towards that. I think it's a great source. My former student Jingdao, who's at University of Pittsburgh, has been doing some work using the camera, but in a contact mode. So he's built a small video game that involves a lot of movements of the thumbs over the camera sensor, and so he gets a simple pulse signal from that data. But the face, you might know there's been work at MIT and elsewhere on recognizing pulse from changes in facial color. There's enough blushing of the face during red blood, I guess what's the word? Infiltration, that's not the word, but there's enough signal from the flushing of the face that you can detect the pulse. And so get at least a pulse signal, a fast stress signal directly from face. And of course, there's so much emotion in the face, and there are a number of toolkits. Unfortunately, a lot of them seem to be proprietary right now. There's a little bit of open source work in the OpenCV toolkit, Open Computer Vision toolkit, that does at least face isolation and a little bit of feature recognition. But anyway, part of the trouble is that there's a fairly significant technical on-ramp for doing vision analysis. So right now we're interested a little bit more in some related topics. We are doing some work in deep neural networks for general image recognition. Might be applicable to this, but for right now, no, we're not doing vision tracking. Do you know of work?
More interesting is anything
Yeah.
indication like the eyeball movements, the blinks.
I would
and
love
this
to
kind of
do.
thing.
I would love to do. Yeah, well, pupil dilation is a very important cue, and I would love to do that, but I don't have the resources right now. Yeah, yeah. I think pupil, especially because it's both a stress cue but also an attention cue, and I think a lot of the work on stress is focusing on these rather macroscopic effects. There are very important effects to do with attention and interest that are more on the positive side. Like you like to know when people are being effectively engaged and having an appropriate level of engagement, not becoming sort of obsessed or, they're staring at this. So they, in a sense, are they in the sort of zone of ideal behavior? That is, they're sort of attending to things without being distracted. I think gaze patterns and pupil dilation, you want the right combination where people are, transitioning from one stimulus to the other without being haphazard, applying appropriate focus. I mean, that's really about detecting whether people are in the zone. That's sort of, ideally, we'd like to move from remediating stress to actually helping people get into the right cognitive and effective zone, I think. So yes, that would be a great topic, but we aren't really there, yeah.
Back on slide 19 or 20, you had plots of the mouse position as a function of time.
Yeah.
That's for your second order model.
Yeah.
It didn't really look like a second order model to me. There wasn't an oscillation or asymptote to it.
Yes,
Is it
well, I'll
supposed
tell.
to look like that?
Yeah, I'll tell you a little secret, which is no. I mean, the detail is that we sort of knew we didn't expect to see really the second order behavior and the gross behavior, and the truth is we don't actually. It's not strictly second order. It's a fourth order. It's 2 second orders stacked, because the gross movement is really not what we're interested in. We're interested in the little second order wiggling that's on the top of it that's at a different frequency. So the truth is we actually do a fourth order model and throw away the lower frequency poles and only take the high frequency ones, which turn out to be in the right frequency range for the system that we're trying to detect. So you're very astute. That's not exactly what we're doing, but it works to essentially filter out the other component.
And when I think about that model, when I move the mouse, am I basically just making a new set point for my fourth order system and letting it settle onto that new set point?
Well, again, it's not exactly a fourth order system. What we understand is when people do a gross motion, it's not, the spring damper is supposed to be a sort of a little open loop system that doesn't have a big input. When you actually move, you really have this other system with a big force input that's responding to that input. So you again don't expect that. And if you look at those poles, they're just not robust. They're all over the place, the dominant poles. So I'm not sure I'm going to answer the question, but yeah, so I'm sorry, what was the crux of the question?
I was just wondering if the model of a motion is kind of like just making a new set point for my dynamic system.
So the simplest biomechanical models are like that. It's basically changing the set point of the system. So yeah, we did try a variety of things that intuitively might have helped, such as trying to only run the analysis during what appears to be a passive phase. You can define passive as energy coming out of the system. And it turns out to have a simple formula in terms of the direction of derivatives, first and second derivatives. So we did it in passive phase. It was not as good. We also looked at active phase. And so I don't know. I mean, yeah, we tried to do the things that might have helped, but they didn't really help. Yeah.
What did you try to do to calm your subjects down during the study? I mean, because I can imagine any experiment is going to make them somewhat stressed over just being in their own home.
Yes.
Probably could have found actually even a greater difference in real life.
Yeah. You know what?
The situation.
I honestly don't recall. So, and you know, it's a research question, which interventions work best for. I think it might have been a breathing exercise, but I'm not completely sure. But yeah, from the work that Pablo's been doing and Mary's been doing, there are clearly different interventions have different effects on different people. So it would be great to have a better understanding of that in the context of this experiment. I'm sure you can calm. We get so many anomalies because some people don't get calmed at all in the calm phase, and some people aren't getting very stressed in the stressed phase. So there's all these outliers which make the data, you know, a lot less clean than we'd like it to be. And yeah, perhaps better, you know, machine learning and modeling, so that you're giving people perhaps the best one, would probably help this data quite a bit.
Second question about the checking for stress inside the voice pattern is, do you think there's a different type of change in the voice during the high-speed version of the stress versus the low-speed version, the cortisol versus the adrenaline type of stress? Because if you didn't know in real life, you don't know when the stimulus is. So if you could distinguish between the two, you can almost figure out when was the stimulus that caused them to be stressed.
Well, so I do know that it's a chronic signal. So, you know, it's the same signal that they find in depression. So it's got to be whatever it is it's in it. It's most likely cortisol because it's basically permanent for depressed people.
But could there be one from the...
There might also be one.
Stress?
Yeah, you would think that somehow that it might also be the same effect, but stronger in a short-term situation. So I don't know if anyone's measured that.
Public speaking experiments.
Yes. Yes. No, that's certainly true. Yeah, no, I mean, the voice is really a wonderful signal, and they're like breathing. The good thing about the work we did earlier is that there are so many untapped signals in vital signs if you're able to get them. It's just that it is really hard to get them. There's definitely a lot more in breathing that people haven't tapped yet. It would be great to be able to do that. We just decided it's much easier to do the work and do the experiments and have impact with the implicit signals, but the signals are often a whole lot more ambiguous.